Hello students, here is the solution to the last problem in the final exams just this December 2023. So by slope deflection equations, determine the reactions at A and D. E is constant. So this is the frame. So take note that at A it's fixed and at D it's pinned. Therefore, for AB, BC, the equation is moment near is 2EI over L quantity 2 theta near plus theta far minus 3 times delta over L plus fixed moment near. But for CD, moment near is 3/4 or 3EI over L quantity theta near minus delta plus fixed moment near minus 1/2 fixed moment far. So for AB, the equation is, this is the first step. Moment AB is 2 times EI 1 over L6 quantity 2 theta of A, which is 0, plus theta B, then minus 3 times delta. This is the deflected shape, expected deflected shape. This is also delta. This is delta 3 perpendicular to CD, and therefore this is delta 2. So this is the triangle relating the different displacements or sidesway deflections. So this is delta, delta 2, delta 3, and that is theta, the angle that delta 2 makes with the vertical, or that's it. So from the figure, 4.5 divided by 1.5 is 3. 6 meters divided by 1.5 is 4. So we can reduce this to 3, 4, 5. So opposite of theta is 4. Adjacent side of theta is 3 and the hypotenuse is 5. So we have for AB minus 3 times delta over L6. There's no load, so no moment. Simplifying, moment AB therefore is theta B over 3 minus delta over 6. Call that equation 1. MBA, so we double theta B, so 1/3 of theta B times 2, so 2/3 theta B. We just copy the sidesway term minus delta over 6. Then MBC, 2 times EI 1 over L8, quantity 2 theta near 2 theta B plus theta C, then minus 3 delta 2 over L. So delta 2 from this relationship, from this triangle, sine of theta 2 is, or sine of theta equals delta over delta 3. And we define sine theta here as 4 over 5. So therefore, delta 3 in terms of delta is 5/4 or 1.25 of delta. Likewise, tangent of theta is delta over delta 2, and tangent theta from this triangle is 4/3, so 4/3. Therefore, delta 2 is 3/4 of delta or 0.75 of delta. So that's why we have 2 times for MBC, 2 times 1 over 8, 2 theta B plus theta C. Since the rotation of BC is counterclockwise, so we treat delta 2 negative, so minus 3 times delta 2 negative 0.75 of delta over L8, then minus plus fixed moment B or BC, which is negative at the left, so negative W 27 L square over 12. Simplifying, we have 0.5 of theta B plus 0.25 theta C plus 9 over 128 of delta minus 144. So we'll call this equation 3. Then MCB, interchange coefficient, 0.25 of theta B plus 0.5 of theta C. Copy the sidesway term, 9 over 128 delta. Then the fixed moment at C is positive of 144. Equation 4. Finally, MCD, because the far end is pinned, 0 moment, so 3 times EI 1.5 over L. So the length is square root of 4.5 square plus 6 square, 7.5. Then quantity theta near theta C minus delta 3 over L. So delta 3 is 1.25 of delta. The rotation is clockwise, so positive. So minus 1.25 delta over length 7.5, and there's no load, so no moment. Simplifying, MCD equals zero point 0.6 of theta C minus zero point 0.1 of delta. Call that equation 5. We then apply equilibrium at B. MBA plus MBC equals 0. So equation 2 plus equation 3 equals 0. So 2/3 plus zero point 0.5 is 7 over 6 theta B. Then plus 0.25 theta C, then plus negative 1/6 plus 9 over 128, that's negative 37 over 384 delta. Then transpose negative 144 to the right, so equals 144. Call that equation A. Then at C, MCB plus MCD equals 0. So that means equations 4 and 5 added. So we have 0.25 theta B, zero point 0.5 plus zero point 0.6, so 1.1 theta C, then 9 over 128 delta minus zero point 0.1 delta is negative 19 over 640 of delta, then transpose 144 to the right, so negative 144, equation B. We then look for the third equation because there are three unknowns here, and that is we extend AB and CD, they meet here. This is the normal to AB, the axial load, shear at A, which is also AX, normal at in section CD, and shear in CD. So summation of moments about O equals 0, but before that, let's locate O, let's solve for Y, then Z. So by similar triangles, Y as to 8 equals 4 as to 3, 4 as to 3, or 6 as to 4.5. It's the same. So y is 32 over 3 meters. Then hypotenuse z as to adjacent of this angle theta is equal to 5 as to adjacent 3. So z is 40 over 3 meters. So having found this, we then sum up moments about O equals 0. Then we'll have shear at A times quantity 6 plus 32 over 3 plus shear at D times quantity 7.5 plus 40 over 3, then plus 20 times Y 32 over 3, then equals the moment of this uniform load 27 times 8 times 4 plus the moment of AB, which is clockwise, MAB. There's no moment in DC because this is pin. Simplifying, so 6 plus 32 over 3 is 50 over 3, so VA times 50 over 3 plus V sub D times, this is 125 over 6, then 27 times 8 times 4 minus 20 times 32 over 3, that's 1952 over 3 plus MAB. We then draw the free body diagram of portion AB. This is the free body diagram. We have shear at A, MAB, MBA. So summation moment B equals 0. V sub A times 6 equals MAB plus MBA. Therefore, V sub A is 1/6 of MAB plus MBA. Likewise, we draw the free body diagram of CD. Summation moment C equals 0, so V sub D times 7.5 equals MCD. So shear at D is MCD over 7.5, or 2 over 15 of MCD. Substitute into this equation here. So V sub A is 1/6 of quantity MAB plus MBA. Then we have 50 over 3 moment arm, then plus V sub D, which is 2 over 15 MCD, then moment arm copy, then equals 1952 over 3 plus MAB. Substitute or simplify 1/6 of 50 over 3, then minus 1 because we have MAB here. So that's 16 over 9 MAB. Then MBA times 50 over 18, that's 25 over 9 MBA. Then 2 over 15 times 125 over 6, that's 25 over 9 MCD. Then we have 1952 over 3 left in the right side. The LCD is 9. We multiply everything by 9. Then this becomes 16 of MAB. 16 of MAB. And MAB is theta B over 3 minus delta over 6 plus 25 MBA. MBA is 2/3 theta B minus delta over 6. Then plus 25 MCD. And MCD is zero point 0.6 of theta C minus 0.1 of delta equals 1952 over 3 times 9. So that's 3 times 1952. So 58, 56 on the right side. Combining like terms, 16/3 theta B plus 25 times 2/3 of theta B, that's 22 theta B. Then 25 times 0.6 theta C, that's 15 theta C. Then 16 times negative delta over 6 plus 25 times negative delta over 6 plus 25 times negative 0.1 of delta, that's negative 28 over 3 delta equals 58, 56. So we have equation C. Solving equations A, B, and C simultaneously, we get theta B 106.414 over EI, theta C negative 172.751 over EI, and delta negative 654.231 over EI. From there, we can now evaluate these moments MAB, which is MA, 1/3 of theta B minus 1/6 of delta. So MA is 144.51510 kilonewton meter. MBA, 2/3 theta B minus delta 1/6 of delta. So 179.981 kilonewton meter positive. Therefore, MBC is negative of that value. Therefore, we can solve AX from here. 1/6 of MAB, 1/6 of MAB plus MBA. And therefore, AX is positive 54.082 kilonewtons, or it is rightward. Then MCD, this one, MCD is 0.6 theta C minus 0.1 of delta. So MCD is negative 38.228 kilonewton meter. So if MCD is negative, MCB is positive 38.228 kilonewton meter. Then we consider BC. RB right is also, when transmitted to this column, is AY or NAB. So summation moment C equals 0, RB right times 8, then plus 38.228, the moment CB, then equals moment BC, which is 179.981 counterclockwise because it's negative, then plus 27 times 8 times 4. Then RB right is 125.719 kilonewtons, and that is also NAB or AY. So AY is 125.719 kilonewtons upward. So we have completely calculated the reactions at A. Then we compute reactions at D. For simplicity, we just consider the entire system. So summation forces X0, 20 plus V sub A, 20 plus V sub A or AX is equal to dx. So dx is 74.082 kilonewtons leftward. Likewise, dy is also RC left. So summation moment about B equals 0 considering BC, RC left times 8 plus 179.981 equals 38.228 plus moment of the load 27 times 8 times 4. So our C left is 90.281. Transmit and draw the free body diagram over here. So we have vertical, this is also vertical. So dy is equal to 90.281 kilonewtons upward. And of course, moment d is moment dc is 0. The other way of computing dx and dy is you solve for shear at d and this normal at d. We, we have not set up normal at D, but you can compute that by summing up moments about A, but it will lengthen the solution. If ND is known, because we can compute V sub D, it is 2 over 15 MCD, then we can just use or resolve shear D and ND into components to solve for dx and dy. But as I said, that's a lengthy process. This procedure is enough.